In this video, we are going to design the singly reinforced beam by using the IS 456 2000 codebook rule. And the problem is, the simply supported RC beam supports a service live load of 8 kN per meter over a clear span of 3 meter. Support width is 200 mm. Adopt M20 grade concrete and Fe415 steel. Design the beam for flexure and shear. Also check for the deflection control. So what they have said? They have said to design the beam for flexure and shear and also check for the deflection control. So in our RCC, what we have to do is the first thing is write on the given data. So the given data are, they are given service live load of 8 kN per meter and clear span of 3 meter. They have given our small l is equal to 3 meter. So I have written the value. Clear span is equal to 3 meter and live load they have given 8 kN meter and support width is 200 mm. So support width is 200 mm and they gave the M20 concrete and Fe415, that is nothing but FCK is 20 Newton per mm square and FY is 415 Newton per mm square. So to start the problem, the effective depth is necessary for all the calculation. So we'll go for the calculation of effective depth. So step 1 is to find out the effective depth. So for that, as per cost 23.2.1 page number 37, what it says we'll see. So this is the page number 37 of IS 456, cost 23.2.1. The vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratio are not greater than the values obtained as below. So basics values are span to effective depth ratio for spans up to 10 meter. So for cantilever beam they have given 7 and for simply supported beam they have given 20 and for continuous beam they have given 26. So now we are designing the simply supported beam. So what they have said, for simply supported beam our L by D ratio should not be greater than 20. They have mentioned. So I'm taking our L by D ratio as 15. So now we need to calculate the effective depth. So I have rearranged it. I moved D to here. D is equal to L divided by 15. So L is nothing but clear span. They have given 300. 3 meter is nothing but 3000 mm divided by 15. So substitute all the values, simplify. We'll get our D value as 200 mm. So next, so I'm taking D as 250 mm. In RCC, often calculated values are adjusted to some standard dimension. So I'm making D as 250 mm. So next is to assume the effective cover, that is D dash. I'm taking effective cover as 50 mm. So it's necessary for calculation of the overall depth, that is D. So overall depth it is denoted capital D. For that calculation of overall depth, you have the formula effective depth plus effective cover. So substitute all the value. We'll get our overall depth as 300 mm. So this is how we calculate the overall depth. So next step is to calculation of the width of the beam. So width of the beam. So for that we have the formula B is equal to 1/3 of effective depth to 2/3 of effective depth. So I am taking B is equal to 2/3 of effective depth. So our effective depth we have got is 250. So substitute all the values, simplify this, we'll get our B value as 166.66 mm. So I am making it into approximate value, that is 200 mm. So our B is 200 mm. So this is how we calculate the width of the beam. So next step is to So step number 2 is to find out the effective span, that is denoted as capital L. So to find out the effective span, again we'll go for the code book. So as per clause 22.2 page number 34, what it says, we'll see. So this is the page number 34, effective span. Unless otherwise specified, the effective span of a member shall be as follows. For simply supported beam or slab. So now we are calculating the simply supported beam. So the effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective depth of slab or beam or center to center of supports, or whichever is less. So what they have said? They have said to calculate the effective span, we should take the clear span plus effective depth. It's one criteria. And the second criteria is clear span plus support width, whatever you got in your problem. So in my problem I got support width, so I am taking second criteria as clear span plus support width. So first criteria is L is equal to clear span plus effective depth, that is they have given 3 meter. 3 meter is nothing but 3000 mm plus our D we have got is 250 mm. Substitute all the value. After simplifying, we'll get our L value as 3250 mm. So and our second criteria is L is equal to clear span plus support width. So our L is 3000 mm plus support width they have given is 200 mm. Substitute all the value. After simplifying, we'll get our L value as 3200 mm. So they also mentioned our L value should be least of these two. So our L should be the least of these two. So which is least? 3200 mm is least. So I am taking L value as 3200 mm. So this is how we calculate the effective span. And the next step is to, step 3 is to find out the load. So find out the load. For that we need to first calculate the self weight of the beam. Self weight of the beam is nothing but our dead load. It is denoted as WD. For that we have the formula B into D into rho. Rho is nothing but density of the RCC, that is constant. The value is 25 kN per meter cube. So substitute all the values. So our B value width we have got is 200 mm. 200 mm is nothing but 0.2 meter. And our overall depth we got is 300 mm. 300 mm is nothing but 0.3 meter. So rho is 25. Substitute all the value. After simplifying, we'll get our value as 1.5 kilonewton per meter. So now the given live load is 8 kilonewton per meter. So to find out the total load, we need to add our self weight of the beam plus live load, that is nothing but dead load plus live load, to find out the total load. So to find out the total load, that is W is equal to dead load plus live load. Dead load which we have got is 1.5 plus live load they have given is 8 kilonewton per meter. Substitute all the value. After simplifying, we'll get value as 9.5 kilonewton per meter. So this is how we calculate the total load. After the calculation of total load, what we have to do is, we'll go for the calculation of factored load, that is denoted as WU. So factored load denoted as WU. For that we have the formula 1.5 into W. W is our total load which we have calculated now. So W is equal to 1.5 into 9.5, our value of total load. Substitute all the value. After simplifying, we'll get our factored load value as 14.25 kilonewton per meter. So this is how we calculate the load. I hope you understood. So next step is to calculate the bending moment. So our step 4 is to find out the bending moment. For simply supported beam, we have the formula mu is equal to W L square divided by 8. That is mu is equal to W L square divided by 8. For simply supported beam, we have this formula. So substitute all the value. Wu is 14.25, which we have calculated. So 14.25 into our L value we got is 3.2 divided by 8. Substitute all the value. After simplifying, we'll get our moment value as 18.24 kilonewton per meter. So in terms of Newton per mm square, that is 18.24 into 10 to the power of 6 Newton per mm square. So this is how we calculate the bending moment. So next step is to calculation of the D required. So whatever the D we have provided, whatever the effective depth we have provided, that is whether sufficient to carry this moment or not, we need to check. For that, I will show how to check it. So step 1 is to calculation of the D required. So for that we have the formula for steel 4 and 5. We have the mu limit formula 0.138 FCK into BD square. And now we have to equate our mu which we have used for the calculation of bending moment, that is W L square divided by 8. And by taking mu limit formula, we need to equate these two. So our mu is equal to 0.18 FCK BD square. So we need to calculate the D required. So I have moved 0.138 FCKB to denominator, and I have taken 2, that is square root. Mu divided by 0.18 FCKB. I have rearranged it. So substitute all the values. So our mu value is 18.24 into 10 to the power of 16 divided by 10 to the power of 6 divided by 0.138 into FCK value is 20 plus our B value is 200. Substitute all the value. After simplifying, we'll get our D required. D value as 181.7 mm. So to carry this load, our D required is 180. So how much we have provided? We have provided our D as 250 mm. So our D required is less than the D provided. Hence our design is safe. Our effective depth is sufficient to carry this load. We have provided the more value than the required value. That's why our design is safe. Now we can easily calculate the further. So this is how we calculate the D check. So after this we'll go for the calculation of the mu limit. So next step is to calculate the mu limit. For that we have the formula same. Mu limit is equal to 0.138 FCK BD square, which we have used for the D check. Same formula we are using for mu limit calculation. So substitute all the value. So mu limit is equal to 0.138 into FCK value is 20 or B value is 200. D is 250. So substitute all the value. After simplifying, we got our mu limit value as 34.5 kilonewton meter. So in terms of Newton mm, that is 24.5 into 10 to the power of 6 Newton mm. Now whatever the mu bending moment we have calculated, so that's less than our mu limit value. Hence, though our mu value which we have got is how much, which we have calculated, our mu limit value is 18.24. So our mu limit value is 34.5 into 10 to the power of 6. So our mu is less than the mu limit. When our mu is less than the mu limit, so it says, by seeing this two, it clearly says that our section is under reinforced. So now we need to design the beam as singly reinforced beam. When our mu is less than the mu limit, it concludes that our beam should be designed as singly reinforced beam. So for this conclusion, we need to calculate the mu limit. And the next step is to we'll go for the calculation of the area of steel required, that is denoted as AST. So next step is to calculate the AST. So step 7 is to calculation of the AST. So for calculation of AST, there are two formulas. There are two methods. One is by simply using the formula that is AST is equal to 0.5 FCK divided by Fy bracket 1 minus under root of 1 minus 4.6 mu divided by FCK into B into D square bracket close into B into D. By remembering this formula, you can easily calculate the AST. So there is one more formula which is given on your code book on page number 96. By using that formula and using the method of quadratic equation, you can calculate the AST. So if you don't want to go for quadratic equation method, so you simply remember this formula, you can easily calculate the AST. The answer will be the same when you calculate the AST value by using the formula which is given on page number 96. Page number 96, the formula is here, that is mu is equal to 0.87 Fy AST into D bracket 1 minus AST into Fy divided by B into D into FCK. By using this formula, you can calculate the AST by quadratic equation. So if you don't want to go for the quadratic equation method, by remembering this formula, you can also calculate the AST. The answer will be the same when you get the AST value by using this formula, will be the same answer when you calculate the AST by using the formula which is given on page number 96 by quadratic equation method. So AST is equal to, so substitute all the value, 0.5 into our FCK is 20, Fy is 4 and 5, 1 minus under root of 1 minus 4.6 into mu we have got is 18.24 into 10 to the power of 6. FCK 20 into B is equal to 200, D is equal to 250. So B is 200, D is 250. Substitute all the value. So simplify this. We'll get auto simplifying. We'll get our AST value as 222.89 mm square. So this is how we calculate the AST. So when you calculate the AST by quadratic equation method, you will get the answer is same. No need to worry. So next, now we need to assume the number of bars to calculate the area of each bar and number of bars. So for that I am assuming 12 mm pi bars. You are free to assume any diameter of bars. I am assuming 12. So now we can calculate the area of each bar. So for that we have the formula AST is equal to pi by 4 into D square, that is 12 square. So substitute all the value. Simplify this, will get our AST value as 113.09 mm square. So now we'll go for the calculation of number of bars. So number of bars, for that we have the formula AST divided by area of each bar, which we have calculated just now. So our AST we have got is 222.89 divided by area of each bar is 113.09. Substitute all the value. So simplify this, will get number of bars as 1.97. So I am making it approximate 2 numbers since we can't provide 1.97 bars, so I am making it 2 numbers. So after calculation of number of bars, we'll go for the calculation of AST provided. So AST provided, we have the formula number of bars into area of each bar. So number of bars is 2 and area of each bar is 113.09. Substitute all the values. Simplify this, will get our AST value as 226.18 mm square. This is the AST provided. So provide two numbers of 12 mm pipe bars at tension reinforcement. So this is how we calculate the AST provided by assuming the diameter of bars and find outing area of each bars and number of bars. So after this there is one more cause, so which is given on page number 46 and 47. So as per cause 26.5.11 A and B, so what it says we'll see. This is the page number 46, tension reinforcement. So minimum reinforcement, the minimum area of tension reinforcement shall be not less than that given by the following formula, that is AST minimum is equal to divided by B into D is equal to 0.85 Fy. So what they have mentioned, our AST, our minimum area of tension reinforcement should not be less than this value. When we calculate it by using this formula on this particular B and D, it should not be less than. So by using this formula we have to calculate the AST minimum. It should not be less than the value which we'll get by calculating by using this formula. So there is one more, maximum reinforcement. The maximum area of tension reinforcement shall not exceed 0.04 B into D. So our area of reinforcement value should not be greater than, when you calculate the value by using the formula 0.04 B into D, it should not be greater than the value which we will get by calculating this formula. And the minimum reinforcement value should not be less than when we get the value by calculating by using this formula. So by using these two formula we'll calculate the AST minimum and AST maximum. We need to apply these two criteria. We'll see one by one. So as per clause 26.5 1.1 A and B, page number 47 and 46 and 47. So the formula which is given on page number 47, I have, that is AST minimum formula, I have written the same formula here. So I will rearrange it. So we need to, now we are gonna calculate the AST minimum, so that I have moved B and D to here. So have rearranged it. AST minimum is equal to 0.85 B into D divided by Fy. So substitute all the value. 0.85 into our B value is 200 and D value is 250, Fy is 4 and 5. So after substituting, so after simplifying, we'll get our AST minimum value 102.40 mm square. On this particular B and D, we got our AST minimum value as 102.40. So now we'll go for the AST maximum. So which is given on page number 47. I have written the formula here, that is 0.04 B into D. So 0.04, our B value is 200 mm, our overall depth value is 300 mm we got. So substitute all the value, simplify this, we'll get AST maximum value as 2400 mm square. This is the AST maximum value. So what they have mentioned, our AST minimum value. So our AST value, so which we have provided, should not be less than the 102.40 and that should not be greater than the 2400 mm square. So our value, how much we have got our AST value? So our AST value we got is 222.89. So our value lies in between AST minimum and AST maximum. So that's why our AST is greater than the AST minimum. So our design is safe. So this is how we calculate the AST minimum and AST maximum. So we have satisfied one more codal rule. So we'll move next. So next step is to design the shear reinforcement. So design the shear reinforcement, what we have to do. So next step is to calculation of the shear force, that is denoted as VU. For that we have the formula WL divided by 2. So substitute all the value. Or W value we got factored we got is 14.25. Our L value is 3.2 divided by 2. Substitute all the value. Simplify this. After simplifying, we'll get our shear force value as 22.8 kilonewton. So next step is to calculation of the nominal shear stress. For that we have the formula tau v. It is denoted as tau v. We have the formula VU divided by B into D. So this formula is given, there is in page number 72, cos 40.1 of IS 456. We'll see. This is the page number 72 of IS 456. Cos 40.1 nominal shear stress. The nominal shear stress in beams of uniform depth shall be obtained by the following equation. So tau is equal to VU divided by B into D. By using this formula, we have to calculate the nominal shear stress. So I have written the same formula which is given on page number 72, that is tau is equal to V divided by B into D. So substitute all the value. Our V value we got is 22.8 into 10 to the power of 6, 10 to the power of 3, 10 to the power of 3 it's. And B value is 200 mm, D value is 250. Substitute all the value. After substituting, we'll get, simplifying, we'll get our tau v value as 0.45 Newton per mm square. So this is how we calculate the nominal shear stress. So next we'll go for the calculation of percentage of tension steel reinforcement. So percentage of tension steel reinforcement, it's denoted as PT. For that we have the formula 100 into AST provided divided by B into D. So don't get confused here. Here we need to substitute the value of AST provided. So this formula is given on page number 72, table number 19. This formula is available. So PT is equal to 100 into AST provided we got is, how much we got? We got here 226.18. So substitute that value, 226.18 divided by B into D. So after substituting all the value, so by simplifying we'll get our PT value as 0.45%.